In this video, we're going to explore the model behind the heating and cooling of standard objects in the environment. And this is Newton's law of heating and cooling. The assertion that Newton made was that the rate at which an object cools off, and that would be represented in an equation by a derivative where h is the temperature of the object, that is proportional to, is equal to a constant times, the difference between the temperature of the object, and notice here we've got a difference, so that's a minus in mathematical form, between the temperature of the object itself and that of its environment. And that's the temperature of the object, and T environment would be the temperature of the environment. This constant of proportionality, alpha here, would be a property of the object involving things as the surface area, the ability of the surface to conduct heat, heat capacity. Those would all be boiled into that one constant to describe the difference between heat transfer from a can of soda, a block of ice, any number of other kind of substances. Well, we have two real scenarios for heating and cooling. We have the object hotter than the environment as one possibility. What we're saying in all of this is that temperature difference between the object and the environment is what drives temperature change. So let's look at the two scenarios, one where the object is hotter than the environment. That means that H is larger than T environment. And that means that the term in our expression here, H minus T environment, is positive. Fair enough. However, if the object is hotter than the environment, we also know that the object is cooling. You put something hot outside, it cools down. And that means that dH dt had better be negative. And if that's the case, we have to make these two things agree. What we have is a negative quantity here equaling a positive quantity here and a minus alpha. Well, we already have the negative sign that we want. The way to put this all together is to have alpha be positive as well. Well, what about the other direction though? What if the object is colder than the environment? Well, in that case, your temperature H of the object is lower than T environment. And that means the term in our differential equation, H minus T environment, imagine you have something out of the fridge at 4 degrees, 20 degrees outside, 4 minus 20 would give us something negative. And at the same time, you take something cold, put it on the counter, the object is heating up. And if that's the case, dH dt must be positive. Well, that's the other scenario we could imagine. dH dt is positive. The H minus T environment, that's negative. And we have a negative sign out front here. Well, we're trying to make these equal to each other. The only thing left for alpha is it has to be positive. The double negatives will already cancel, and I don't want to mess that up. So we're going to need alpha to be positive as well. One way to think about this is to think about the properties of something like a thermos container. A thermos container keeps hot things hot and cold things cold. And what we're capturing with that is it doesn't matter what direction the heat transfer is going in. The properties of that material, of that insulating barrier, of that surface, those are not going to change whether we're heating up or cooling down. And that's captured by the fact that this number here, this constant, doesn't change depending on the scenario. It's a property of the object we're looking at and not about whether it's heating up or cooling down. The rest of the math takes care of the direction of heat transfer. Let's make this more concrete. We're going to put a potato at room temperature into an oven at 200 degrees Celsius. So our T environment is 200. Suppose that we have an alpha value already given to us, and we're going to measure T in minutes. What we want to do is write the differential equation describing the rate of temperature change of the potato. So the first thing is to recognize that the potato temperature is changing over time, so we include this bracket T here. And if that's the definition for H, then we can simply use the law of heating and cooling here. The derivative of H is going to equal minus alpha H minus T environment. The rate of temperature change is proportional to the difference in temperatures, but we actually have values for a lot of these now. So minus 0.25, noting that we are using a positive value for the alpha part of this, There is a negative sign, but it's being kept out front. That's our positive alpha. And we also have the environmental temperature at 200 degrees Celsius, so we include that as well. There is a temptation to include this 20 degrees in this formula, but remember this is true for all time. True for all time. However, h equals 20 is only true at t equals 0. Only true at one time. So we shouldn't confuse those two ingredients. The differential equation is always going to be playing a role, but this particular feature is just a starting pattern, often called, an initial condition. It's a lovely piece of information, but it doesn't affect the differential equation, which happens or applies even after the starting temperature has been set and then changes as the potato is heating up. We now have a differential equation that governs the rate of change of temperature for this potato. We're now going to solve it using our separation of variables. One of the techniques that we have in our toolkit for solving differential equations. We start off with the differential equation written out, and we then identify the variables. We have h and an h here. We also have a t, but the t doesn't have any other t's, so that's fine. Give it a different color here. What we're going to do is move the t's over to the right and move the h's over to the left. And there's some choice in here. We try to leave as much as possible on the right-hand side if we can, because we're eventually going to put everything back on the right when we're done. So what I'm going to do is leave that negative 0.25 on the right, bring up the dt, and we're going to have to take this entire expression here and divide through by that. We can't just take the h by itself by dividing. So we're going to end up with h minus 200 on the left-hand side. Notice what we're doing here is we're separating. H is only on this side, t is only on this side, and we then integrate. Integral, integral. Just being careful about those steps. This is a linear function on the bottom. It's like 1 over x. So we're going to get ln absolute value of h minus 200. We can double check when we differentiate, we get back to this. The right-hand side, we end up with a constant with t as our variable, means we have t as the multiplier. And both integrals could have their own plus c's, but we can agglomerate those into a single plus c on the right-hand side. Last but not least, we're going to solve for h, the temperature of the potato. So we're going to solve for that. It's hiding inside this ln, so we're going to need to exponentiate or use both sides in their entirety, and this is important, as the exponent for a base e. When we do it on the left-hand side, we get this lovely cancellation because e and lns are inverses. On the right-hand side, we get two terms, e to this whole thing plus c, which we usually break into, and you'll see why in a second. A sum of exponents is the same as multiplying on the main line, so that second expression turns into multiplied by e to the c. Now comes the fun part. What we're going to do is invent a new variable, create a new variable, define a new variable, call it a, and it's going to be equal to e to the c. That's going to simplify that expression there. However, there's also these absolute values that we'd like to take away so that we can solve for the h, and the idea is we just do that all in one step. If this expression was negative, we would make this value here negative as well and call it a. If this was positive, we wouldn't do anything. We just leave it as e to the c. The result of that replacement is that we have h minus 200 equals a e to the negative 0.25 t. We've gotten rid of the absolute values, and we've tidied up that e to the c into a single constant. Last but not least, we can solve for h, bring the 200 to the other side, plus a e to the negative 0.25 t. What this is called is our general solution, because it actually covers the case of any possible potato being put into a 200 degree oven. However, it's not describing the specific scenario that we're talking about, which is the scenario where we start the potato at room temperature, specifically at 20 degrees. We can include that information now though, and it'll let us solve for a. Use the initial temperature at t equals 0, h equals 20 to find a. And if we do that, we plug in h, that will be 20. That's going to equal 200 plus a. We're plugging in t as our time value when we have 20 degrees times 0. That gives us, bring this over, negative 180 equals a e to the 0. Well, a e to the 0 is just 1. So that's our a value. So our solution for this particular potato is 200 minus 180 e to the minus 0.25t. And that's something we would call the specific solution or the particular solution. That works with the temperature at time 0 being 20 degrees. All right, that's not a bad accomplishment. Having looked at a new field and now being able to predict what's going to happen using a fundamental law of science and some integral calculus to predict into the future what's going to happen to this object in this scenario. Having found the solution based on formulas using the separation of variables, it's also helpful to compare with the other technique we've seen, the graphical technique of using a slope field to sketch the same graph. Now we can do that fairly quickly here because h is the only variable that shows up on this side, and what we're interpreting this as is the slope on the h versus t graph. So we have a graph down here already sketched out, and this part here then becomes our formula for slopes on that graph. We'll take a few sample temperatures, and then we'll calculate dh dt, and let's keep it simple. We'll set some evenly spaced numbers here, which give us slopes of negative 0.25 times minus 200 here, and that would be positive 50. What that indicates is on this graph, we'd have a slope of positive 50, which would be heading for here. Every time the slope, rather every time the h value, every time we talk about a temperature of 0, and so on. If we have a temperature of 100, we're going to end up with negative 0.25. 100 minus 200 is negative 100, and that will be positive 25. Those slopes would be up 25, that's the time it takes to cross 1, like so. Whoops. Keep them consistent here, and so on. What we see is a shallower slope than the 50s, and when we have 200, we end up with 200 minus 200, which is 0. At 300, we're going to have negative 0.25 times 300 minus 200, that's positive 100, or minus 25 when we're done. So if we add those, at 200, we have 0 slopes, flat lines. At 300, we have the minus 25 slopes, down by 25, over by 1, and so on. If we take a look at that, what we see are solutions that look like this. If we started at 100 degrees, we'd go up, but we'd flatten out before we reach 200. And if we started at 20 degrees, which is our example in this problem, we would go up and approach the temperature of the oven, 200 degrees. Notice if we started above, if we had something hotter than the oven, a little unusual, but certainly possible, we would have the same kind of shape, except it would be decaying downwards towards that 200 environmental temperature. We can then match that back quickly to what we've seen in the formula. If we look at our formula, we can see that, interpret that formula here as the difference from 200. In other words, we're at 200 basically, but then we're going to have a difference from that, and that difference from 200 shrinks exponentially. There we go, because of this exponential multiplier here. And that's what you can see in the graph. We have a difference of a negative 180, and that gradually fades over time until it approaches 0, and we're left with the 200 environmental degrees of the oven.